Jordan is here. Michael. Hello, Michael.
Hi, how's it going?
Good. Yeah. Hello, Moses. How's it going? Good. Good. That's Luke. Who else? 1, 2, 5. Yeah, right. That's it.
I had a quick announcement for the
Yes.
ones in quantum mechanics.
Yes.
I have a copy, a PDF copy that Moses gave me of the Valentine book for quantum mechanics. So if anybody would like a copy of that, let me know. Or I can just send it to you because all of you are nodding.
Yeah, that sounds great.
Yeah, I'd love to have a copy.
It is just the first edition and not the second edition. But I don't think there are very many substantive differences.
Yeah, I think he focuses on just the theory and doesn't worry about what specific edition. I think in our opening class time, he said, you know, the older the edition, the less it's going to cost you. So,
Right.
but that one 3-volume set that he recommends highly is a expensive set. They just reprinted it in 2019. Cohen and I forgot the other author. They're French.
Technology.
Yeah,
like
Cohen.
$450 for the set.
Yeah.
If I do that, I'm going to have to let my wife get another dog. Or 2.
That's a bargain. Yeah. And what is more frustrating is that these publishers come up with new editions, really minor changes. Sometimes it's just adding exercises, let's say even about 10% exercises you add or change. It's a new edition.
Luckily for the high-level books, they don't come out because it has such a limited audience. But trig-based physics, calc-based physics, every 3 years.
Yeah. I feel it's fast. And the worst is when they come up with a new edition and there are more mistakes in that. Part of you don't have it in control. Okay, so let's do something. So we have homework 1 due on Tuesday. What's the date of Tuesday? 21, 28, 26, I suppose.
Yes.
So today I'm going to zoom out again like the last semester, and you guys tell me which ones you prefer. How was it last on Tuesday? Was it any better or was it the same?
I thought it was really nice. I didn't have to strain at all to see what you were writing.
Okay.
Yeah, me too.
Strong comment like that really helps. And I did, I was thinking about it. I think Jordan, it was you who mentioned that it is fuzzy. It's probably because the pen I use doesn't stick to this glass so much, all the way I write. I can see that there are patches in there. So I'm thinking of getting this really thick pen, which might help. That might be the problem.
It might contribute to the problem.
That might contribute, yeah, that might not be the only problem. There are so many parameters, agreed.
If you look at the edge of the board itself.
That's also fuzzy?
Yes.
Okay.
It's just the quality that it's being recorded in. It could just be a Zoom thing. I don't know.
Yeah, sure. Okay. So at least the pen part I'll try to solve. The small part. Okay. Let's try to zoom. Give me a few minutes. Okay, I think for now, let's stick to this board. We'll come back and set that later. Okay. So we're doing magnetostatics. There are four Maxwell's equations, only two of them, or two of them really get decoupled with the electric part of it. And we noted that the equations are the divergence of the magnetic field has to be 0, and the curl of the magnetic field has to equal to the current density. Usually we write del cross H is equal to J, but replace it with D, and then that is me not having J in there. A couple of things immediately come out. Since divergence of something is 0, and this equation is true anytime, even not in statics, that's always true. So this immediately implies that B has to be, or B can be written as a curl of a vector potential. And since this is a curl, we can also say that this has a gauge dependence now, right? I mean, I can add a gradient to that and nothing will happen, so it will stay the same. So it is it's slightly a bigger version of electric potential. Electric potential you can only change, right? There is a constant change and you can get away. You cannot detect that. But now this is a bigger change in the sense you can add any gradient of an arbitrary function to vector potential and it stays the same. That means to say, so this is called a gauge dependence. I can say A prime is equal to A plus the divergence, or not the electric potential, sorry. So phi usually we say is electric potential. So this is some arbitrary function of position and time, not just time. This is arbitrary. and magnetic field will remain the same because curl of this piece is 0. Right? So So the freedom is slightly more complicated than what we had in the electric case. There's a similar relation you can get here. If curl of something is a vector, right? If I take the divergence of this would be 0 on the left, right? Divergence of a curl is 0. That surely immediately implies that 0 is equal to J. We usually write it the other way, but and that's a requirement for the current density, that it should be divergence less. So you can only talk in terms of loops of currents, which it shouldn't have a source anyway. So these two come out of this, and there is a gauge freedom here, which also means that if I had to put this in here, there's a gauge choice if you want. So there's a choice. We work in a choice. Also, let's say this is as of now very general. Right? So now let's say gauge choice. We'll stick to this gauge choice, but we will see that when we release, when you're working in magnetostatics, there's a choice that's convenient. When we do dynamics or the radiation part, we will have a better or another choice that will be convenient. And so the choice would be that the divergence of the vector potential has to be equal to 0, right? So that will be magnetostatics. So basically these two equations, but there are so much implications there. So magnetic field can be curl, divergence less source of current, and divergence less vector potential also. And remember, divergence less means that these things cannot come out of a point. Right? There is no source for these quantity. That's the way to interpret it. And curl means, think of it as coils, so like circular field lines. Okay, that's one thing. And based on this, we argued that if I were to substitute this into this equation, so very quickly, what we did was del cross of del cross A is equal to mu naught J. Right, that was what we did last time. I can open up this bracket using vector identity. Square A is equal to mu naught J, but in our gauge choice, the divergence of A is 0. So this is let me know when I'm crossing the board. Oh, I already crossed. So, okay. Is anyone speaking?
That was out in the hall.
Oh, okay. But that's a Laplacian. We know how to solve a differential equation if there is a Laplacian multiplying something and that is a source. So this is called the source. This is the field, and that's the Laplacian. And then you use the Green's function idea, and you won't go into the details of that. Immediately we can use it because in the last semester we spent time on it. So vector potential immediately is mu naught over 4 pi d cube r prime J prime over r minus r prime. Think of vector electric potential due to a point charge. That's the Green's function. That's 1 over r minus r prime, right? If you have a charge at r prime, that's the electric potential. since we have the same Laplacian, oops, it's not along for some reason. So that's the electric potential due to a point charge, but since it's the same operator sitting there, it's the same potential that shows up, but now this acts like from a current, right? So this is a, you can say magnetic potential due to a small line element of charge. So think of a tiny element here. So that's d cube r times j. Right? So that's the tiny element there. So that's the contribution from that. And then you keep adding that. So you get all the contributions from all the pieces. And what are we talking about? So that's the current I. And that could be, the observation point is here. So this is vector r, and that's r prime. That's observation point, that's your source, and you integrate over all these sources. And you get the vector potential part of it. So in a sense, this is the vector potential due to a magnetic vector potential due to a tiny current density. And we want to calculate the total. Once you have the vector potential, we can calculate the magnetic field. And the few things you have to check, we can verify that what is a magnetic field. We should be also able to check what is the divergence-less property here. And we should also see whether the B is 0 or not. So that's all part of your homework, but I'll do a couple of them here so that you get a feel for how to proceed. So again, we have A is equal to mu naught over 4 pi right. Let's check if the divergence indeed is 0. Before we proceed, it should be clear that there are two R's here. One is the position of the observation point, and one is the position for the source. Even though it's an integral, it generally say that an integral parameter doesn't have meaning, but that's a source. You're integrating on R prime. And this derivative, that could be two gradient operators in that sense, right? So that could be a gradient and there could be a gradient prime. This acts on R, this acts on R prime. In principle, there are two, but this one acts only on R. And our understanding is that that represents the gradient operator with respect to R. So where does it act on this? It acts on the denominator, wherever this R, that's the only place where it acts. There is R prime, 3 places, but this is an integral, but the gradient acts only on that. So that's one observation. So that means, first of all, it can go inside because the integral is with respect to prime. So this is d cube r prime. Move your j a little to the left so that I can. And this is dotted, dot product. It doesn't matter in what order you write. So that's 1 over r minus r prime. Hopefully that's clear. Because it acts, and this acts only on this. Okay. And that leads us for us to ask the question, what is Now, one can, there are a couple of ways to go about this. We can actually operate this. We know how to do this operation. So just as an exercise, I don't want to do this, or I don't want to go along that path, but still, it's good to remind ourselves, what is this equal to? Like after the whole semester, so this is one of the, what is that equal to? What is this equal to? 1 over r, physically? 1 over r minus r prime? What is it related to? What does it remind you?
This scalar potential.
Scalar potential, yes. So gradient of scalar potential, what should that be equal to physically again?
The electric field.
Electric field of due to a point charge. So that should immediately give you the answer there. But now suppose I ask you, how do you do this? Now you know the answer probably in your head because Moses told that it is the electric field due to a point charge, right? Except that Q you remove the Q and other things. So how do you operate this and how do you get the answer here? What is this equal to? Let's just simpler one, how about that? What is gradient of R? No?
Minus 1 over r squared.
Yeah.
Epsilon over R squared.
Minus 1 over r.
Oh, minus 1 over R squared. Yes, yes, very good, yes. Is that all? That's a vector, that's a scalar, so there's something more to it.
R hat.
R hat.
R hat, and how you get that is that, so there is minus 1 over, first you operate this, and then you have to take the gradient of the chain rule, right? First you do the 1 over R, and then you have to operate on R itself. And this is R hat. Right? So that's equal to minus R hat over R squared, which is the electric field up to a negative sign. If you put in the negative sign, it has a structure of the electric field with a point charge at the origin, right? But now we are moving the pointer. We don't want to keep it at the origin. It's still in the space. No. So what will this be? 1 over r minus r prime. Same idea. First, differentiate this. So that's minus 1 over r minus r prime. And now the gradient has to be r minus r prime. So that's a r hat of this quantity, but it's hard to write that. So you simply write r prime over r minus r prime. This is a square. Like that's a unit vector with respect to the r prime, right? That's your, that's how you would operate that. And you can substitute that in, but then you have to worry about how do you do that integral and so on. It's not very convenient. So we want to go around a different path. Notice what is the answer here? Divergence of A. We expect it to be 0, right? Or we would like it to be 0. So let's think of how else we can go. So let me go back. So this is one challenge. Is zooming in. I keep moving around. Okay. So this was just a reminder. Somehow I would like to show this to be 0, but notice that divergence of J is 0. So somehow if I can use that, but it turns out that this is not divergence of J. It is not even acting on that. It is acting on the other quantity. So can we somehow use some tricks to make this operate on the other side, right? So that's what we are going to show. So notice that for that, what is d by dx of, let's say, exponential of x minus y. Right? So this is equal to this x on x, and you get exponential of x minus y again, right? That's all. But what is derivative with respect to y now?
It's minus.
So it's minus of that. So this is minus of e raised to x minus y. Right. In general, you might be able to convince yourself in the that d by dx of any function of x minus y, like it could be log, tangent, build any function you want. This will always be equal to minus of d by dy of the function of x minus y. Is that convincing? Is there any?
Yeah.
Right? Okay. Yeah. Okay. I don't know any explicit proof of that, right? So I think the example is the best I could come up with. Okay. Which means that, so now if I go to gradient, right, gradient of 1 over r minus r prime, so magnitude also works the same. That should be equal to, I should be able to change the gradient operator. This is minus gradient prime acting on 1 over r minus r prime the other way. So I switched from, instead of acting on r, I'm now acting on r prime. Why do I want to do that? Because somehow I want to act the gradient operator on j, but still it's not acting on j, it is acting on the other side. But now I can think of moving it on the other side, right? So I have the divergence of A is equal to mu naught over 4 pi e cube r prime and j of r prime doctored with, and there is a negative sign now, right? So there's a negative sign, I put that here, negative sign, and del prime now. How can I really want this gradient operator to act on j. How can I do that? Any ideas?
Use the product rule.
Yes, yeah, product rule, what is it called? Integration by parts, you would, right? Which is basically because of the product rule.
Yeah.
Yeah, right. Good, very good, right? So use the product rule. So, so I basically want to bring it out. So I'll do it exactly like the product rule. So this is d cube r. So product rule says that act on both. Notice that this is acting on r prime, but I'm going to bring it out, but I have to take the dot also, right? So this is the dot product is with the j. So that's j r prime and 1 over r minus r prime. But that's not correct for sure, because in this, the top expression, this is acting only on this, but now this is acting on both. So I have to subtract out whatever mistake is going on. So I have to subtract out. That involves adding something. And now I act only on j, right? So I bring this out on this side, move it around, and that's L prime of j or prime. The second term is 0, right? Because we know, or we concluded that the currents that we talk about cannot have any source, because if they have, then you're talking about dynamic. Then that is not consistent with statics. At least then we have to use approximation to get away from them. And what about the first term? Then we are stuck with the first term. That should also be 0. And that will be zero because, or how can it be 0? This is a total derivative, like there's an integral. That means it will only contribute at the boundary of our universe. Let's say if we are integrating this on all space, so this will be only on the boundary. And you say that the current, there are no currents at the boundary, right? So we require that whatever current is there is at all at a finite distance. We don't have any current sources at infinity. So this is a boundary term which you have to impose a condition that our sources, there are no sources at infinity. So this is a boundary term which we argue that doesn't contribute. So these are the tricks you want to use in your homework problems. That one is, of course, you should be able to operate this out. Second is you have this trick that you can switch from R to R prime, the operations, and of course integration by parts. Using these 3 tricks, you should be able to do the first couple of problems. But that's okay, but we are usually interested in the magnetic field, right? So let's go to the, let's calculate the magnetic field, and then we will do an example. How should I set this?
So the minus part is equal to 0 because the green function gives,
No, because we say that we require that the current density, there is no current density at infinity. So why is it 0 again? So notice this is a total derivative.
Mhm.
So that means this whole integral of a derivative, it survives only at the boundary. That's because of the following reason. So if you have a dx times d by dx of a function, right? Can you read that? Yes.
Yeah.
Right, and it goes from a to b. This is equal to f of b minus f of a. Right. This kind of integrals survive only on the boundary. Right? And this is a total derivative. So there is a d by dx contribution to this, d by dy to this, and d by dz to this. Each one of them will have this structure. So that means it is surviving only on the boundary.
okay.
And the boundary we say is the boundary of our universe, or whatever our boundary is, we require that there are no currents at the boundary. So that's a requirement we are making. It's a reasonable requirement that at the surface of our universe there is no sources. That's typically reasonable. Okay. Clear? Okay.
Yeah, thank you.
So we again have the magnetic vector potential given by this formula. And this is J of prime. And what is the difference between what we will be doing here and an introductory level physics is that we will think more in terms of vector potential than the magnetic field. It helps to connect that. That will be the new part, but there will be a lot of things that the ideas you will be able to bring in. So what is a magnetic field? Equal to, so that's the curl of the vector potential. So if I take the curl of the first term, I should get the magnetic field. Curl of this, so this is acting on R. That's mu naught over 4 pi e cube R prime. Fine. This acts only on R. So since there is a curl, I don't want to move the J on this side. Instead, I move this to the left. Right. This acts only on that. Right. This acts only on this R, not on R primes. And there is a curl. So this is curl of J. Is that clear? Like this operation acts only on this R, so I can move things around. And this parenthesis puts in that condition, oh, this is acting only on this, it's not acting on this. So that parenthesis is but this we already know how to operate. A few minutes back we did that. That's the electric field due to a point charge at R prime. So that's equal to, that's a minus sign coming from there. I put that minus sign in the front. 4 pi e cube R prime, and this was R minus R prime. No, this is no magnitude, that's real vector. This is in parentheses, divided by R minus R prime cube. Right? That's the electric field due to a point charge at R prime, except for the charge Q and 4 pi and all that. And this is crossed with J. Fill up. It's equal to just want to rewrite this, that's all I will do. So this is use the minus sign to change this cross product. Okay, that's the expression for magnetic field. That's what we will use whenever we want to calculate the magnetic field. Have you seen this before? In introductory level physics, in some form, it's slightly. And what is this called? If you have seen it, the name for it.
Use of R.
Yeah, exactly. Yes. So how do you pronounce that, Moses? You seem to be correct.
I don't know, I said Bios of R.
Yeah, I think that's what it is. It's bios. I always said it bias, so I used to pronounce it P. Apparently, the P is silent here. Yeah. But typically, how it goes is that you don't, like when you're doing introductory level physics, you don't work with J so much, right? So I just, so what's the connection in there? So it's good to point out. I'll come back and maybe tell it in more detail, but A simple way of looking at it is that, remember, our current density is current density, right? J is current density. So it's J dotted with dA, right, is equal to current. Right? So that's the way to look at it. But this is volume. So what you want to do is that, so the connection here is that, or let's say the correspondence here is that d cube r times j is equal to dl times I. So I multiply by the length element here, multiply by the length element there also. But here, one has to be doing that very carefully because now we are writing the vector relation there. And usually you see that as, let me see. So perhaps our the way we do it in introductory level physics, I think, is because we always talk about sources in terms of current, we never talk about charges, a single point charge. So this is written as dl, so dl times I, let me write idl, crossed with, is that correct? This should be more familiar. I think this is how it's.
Except at the early levels, they don't do the r minus r prime, you just get an r.
That's also right. Yeah, you would just write r over r cubed. Yeah, that's correct. That's because typically we do very simple examples like that. Here also we will be doing simple examples, but especially for a point charge, it's good to keep this. So for example, usually we now talk about if it's a positive charge, does it have a magnetic field associated with it? A point charge Q?
No.
No? Yeah, but no? But you want to say something more to that. That should be a sentence added to that, right?
Is it moving it or something?
Yeah, if it's moving or something, correct? But if it is moving, then it can have a magnetic field. So typically there is no magnetic field, but the moment it moves, then it depends on a frame, then they should have a magnetic field, right? So then the question comes, what is a magnetic field associated with a moving point charge with respect to, let's say, lab? Like with respect to lab, a charge is moving, what is the magnetic field associated with that? So let's try that. That should be straightforward, one would think. First, let's see, we can also get A, right? So that raises the question. So this is a moving point charge, or point charge, let's just say point charge. Point charge, what is the charge density? Let's say R prime is equal to, what's the charge density due to the point charge?
It's a delta function.
Yeah, the function, right? So it's a charge Q multiplied by the delta function. But then I have to specify the position of the charge. So that's equal to, let's say RQ. So this is the position of the charge, right? R subscript Q. And it's a function of time, but let's say it's just moving with constant velocity. So position of the charge is moving in principle. So it is V times T. Since it's moving, we can also say RQ is equal to, if it's moving with constant velocity, it's just V times T, right? Derivative of RQ will then be equal to the velocity. Right? What's the current density for a point charge?
we're just integrating?
No. How you get that is that you just multiply the velocity. It's like a flow, right? Flow of charges is the current, right? What's the connection between them? It's tangentially whatever that point is, you get that velocity. So you usually just multiply by velocity. So it's Q. It's first of all, simply speaking, it is velocity of the charge. Right? So let me say V of Q here. So velocity of the charge times the charge density itself. So it is equal to V of Q. Let me get rid of the subscript for a while. I'm afraid that I confused with the charge itself. It's Q times V. Good. But once we have charge density, we can just plug it in our relations and get the vector potential, we can get the magnetic field and so on. So let's see what's the vector potential due to point charge, right? Vector potential due to a moving point charges. Let's plug this in our equation. Mu naught over 4 pi d cubed r prime, and J now has a nice formula, right? So there is J divided by r minus r prime. So that is J here. But I'm going to replace this J with my point charge. So that's Q times V times delta function r prime minus RQ. Right? But that's an integral that we know that's one of the easiest integrals because it's a delta function. There are 3 delta functions. All of the integrals go away, and we just have to replace r prime with RQ. Wherever r prime shows up, I'll replace it with RQ. So that's equal to mu naught over 4 pi Q times V divided by Is it visible? Oh, no. Just for reference, it is good to remember what's the electric potential due to a point charge. Electric potential due to a point charge is equal to 1 over 4 pi epsilon naught. And if it is not at origin, it is 1 over r minus RQ, right? And that is charge Q. That is Q divided by this. Right, so you just multiply by that velocity and notice how the epsilons and mu's work there. That's because of the speed of light that shows up. That's nice. What about the magnetic field? Let's see the magnetic field. Now there are 2 ways of proceeding with the magnetic field. Either we can take a curl, right? So magnetic field, there are 2 ways. Either I can take a curl of this quantity, or I can use my formula with J there, right? So there are 2 ways, and both should give the same answer. Let's plug it into the integral formula, mu naught over 4 pi. That should be a quiz, right? Yeah, I'll put that in a minute. This is dq r prime, and J is Q times V times delta function, r minus r prime minus Q. And that's your J crossed with r minus r prime q. Again, the delta function is straightforward. Do it wherever you see r prime, replace it. So that's q mu naught over 4 pi times q time. So there's q. I think it's good to think of it as, yeah, let me write it. Q times v crossed with r minus r cube over r minus r cube magnitude cube. Remember your electric field due to point charge is 1 over 4 pi epsilon naught r minus r cube over r minus r cube cube. Let's write it in terms of the electric field. How about that? So this is equal to, in terms of the electric field, that should be a q there, right? So q 4 pi epsilon. So there's a mu naught, I multiply by mu naught and then epsilon naught, right? And then everything else is electric field. So that's V crossed with electric field at that point due to the point charge. What is mu naught over epsilon naught? So that's c squared, correct? So this is so the best way to write this is c times b. So remember your 1 over mu naught over epsilon naught is equal to c, right? So let me multiply a c on the left and one of the c's I will write it underneath v because that's how relativity comes in. So v over c crossed with an electric field due to the same point charge. And that's a generic thing we are going to be seeing again and again. In this whole semester, we will see that often, not always, often the magnetic field, especially this kind of, whenever a relative motion is involved, if you know the electric field, how is the magnetic field generated in a moving frame, it is usually V cross E, with the units taken care of in this manner. Dimensionally, remember that force is equal to Q times E plus Q times V cross V, right? That gives you the dimension of electric field should have a velocity times B in it, right? This is dimensionless, so dimension of electric field has a velocity C times B. So dimensionally that balances out. That is the reason why I wrote the C on this side. You can of course write that C squared, that's perfectly fine. But always the construction is C times B and electric field have a similar properties. Of course, you don't have to go through this. You can start from A. So calculate del cross A for a point charge. So start from here and do this, right? So that's a quiz problem. So start from A, not this, right? This
Can you raise the camera?
Oh, yeah. Thank you. Yeah, do that. Yeah. Yeah, so the first problem is start from this relation that we got for the point charge and operate the gradient right away here. We know how to operate that, and you should get the same answer, right? You shouldn't get two different answers. So just that should be a small, simple exercise. Okay. Any comments or questions? we did a point charge, and the next example one can do is a straight line, right? A current carrying, let's say finite straight wire. Is that correct for straight? It's good. That's an edge there. Okay. By finite straight wire, I mean it's just this. The current I through this. Right. And let's begin by reminding ourselves, if this was infinite, a long straight wire, what's the magnetic field associated with this? Let me write it here. I think there is this. What's the magnetic field due to an infinitely long wire straight?
Mu naught I over 2 pi.
Mu naught I over 2 pi
R.
r. So basically the distance from the wire. So let's call that rho, because r is the spherical coordinate. Rho is a cylindrical coordinate, which is only in that plane, right? And the vector scalar. So this is circular, right? So the magnetic field lines are circular due to this wire. So let's use phi hat. Right? That's what it is. So that's what we should get. So that's a very simple answer. But let's, what if it was finite? You guys remember my answer? So what if this was finite now? What changes? So let's say this 3 dots and dot. So magically the current begins from one point. There's a source of a current, there's a sink of a current. Right away you would say that, oh, magnetostatics doesn't allow that, right? Because we said divergence of J has to be 0. That's not okay. But for a moment, let's keep this. So what we'll do is that we will do this, but then we have to restrict ourselves to some small region here. Right, so we're very far away from the sources. So it's like saying that the sources are at infinity, so it's all going all the way there. So it's not a good thing, but if we don't do it, we will have problems with the electric potential, because then they will diverge. So we're going to tweak this in this fashion and take some limit and see that how far we can go with this, and we will go pretty good. At least I will be able to isolate what was the problem creating issue, right? But in elementary courses or in introductory level physics, we do this finite wire, right? And what's that? How does this change? Right? Any idea? So it's a simple extension that comes up. You say that suppose your observation point was somewhere here, like in introductory level, or mathematically speaking, you can even go beyond, even though I'm going to restrict ourselves to this region because that's where we are doing statics, so we shouldn't have these sources. But so if you're somewhere here, let's say, then there is a, so there is this angle you will form, so it's theta. So this is theta. That's theta 1. So that's your observation point, by the way. That's your R. And that's your theta 2. So if you have those two angles, then this comes out to be just a small extension, sine of theta 1 and minus sine of theta 2, or sine of theta 2 minus of sine of theta 1. And clearly you can say that in the limit when theta 2, when this point goes to infinity, like when for an infinite wire, theta 2 goes to pi by 2, right? And theta 1 also goes to pi by 2. And this this formula allows you to talk about half wire. Like what if this was starting from origin and then going all the way to one way to infinity. So then one of them will go to pi by 2, the other one is 0, right? So you can talk about half wire or quarter wire. Like there are many things you can do with this formula. Notice the negative sign, you should be careful about that. Sometimes certain books write it as positive, but then their understanding is that they have taken care of it. So be careful about it. Okay, but that's all reminding yourself of how you go about this problem. But we want to do this, we want to first of all get the vector potential, right? Which is a harder way, harder thing. Like same thing with when you did a electric field due to a wire, that comes out very easy. But the electric potential due to a wire, that is not convenient. Okay, with that caveat that this is actually having a source for a moment. So we are thinking of it as very large. So that is, let's say this is the origin. So this is 0, 0, 0. Right? And let's say this is 0, 0 minus L. And that's 0, 0 plus. Right? And L is large. Right? We want to talk about L tends to infinity, but we don't want to right away put it there because in the blunt form, it causes or it doesn't show up where exactly the form of the divergence is. Okay, so we have to start with J, right? Our expressions depend on J. So it's like once I get the charge density in electric field, then I can do the calculations. Now, what is J for this? I'm saying there is a current I, right? So there is I going through, and it's let's say this is on the z-axis. So that's your z. So the direction is z hat. Current density is current per unit area. So current is I. The area, this is an extremely thin wire, so its area is pretty much 0, right? So that will be captured using delta function. So this will be delta of where is the wire situated? That's at x equal to 0 and y equal to 0. Remember, delta function is 1 over a very small, delta function is very large at 0. So that means it's 1 over a very small quantity. So that's the area. So this should be thought of the delta x, delta y should be interpreted as 1 over small area. Its dimension is 1 over length, remember. Right? So it's the area of the wire, the area of wire. Is that clear? Any, like at least to get a physical feel for so that's your J. And since it is R prime, let's say this is X prime. I said R prime. Okay, that's your J. Get the electric potential. Sorry, vector magnetic potential or magnetic vector potential is equal to mu naught over 4 pi d cube R prime. So which is the same as dx prime, dy prime, and dz prime. And minus infinity to plus infinity, minus infinity to plus infinity, and minus infinity to plus infinity. And J, oh, there is a small error in J. What is the error in J? I'll come back to that. So J is nothing but z hat I delta of x prime delta of y prime divided by r minus r prime, right? Magnitude of r minus r prime, which is nothing but x minus x prime square plus y minus y prime square good. But I said there is an error in J. And the error is that this is for an infinite wire. Where is the information about the length L of the wire in this? This is supposed to stop in the z direction. So I have to put some step functions there. And I will say this is a function which survives, which is equal to 1 if you are on within this part of the axis. It is equal to 0 if this is not satisfied. It is equal to 1 if this is satisfied, 0 if it's not satisfied. And that will, so for example, if I were to take divergence of J immediately, they'll have trouble because this will survive now. So maybe a simple exercise. Yes, simple exercise. Let's talk about infinite again. L tends to infinity. L of J is equal to, this should be 0, right? If it is infinitely long wire, then that should be 0. How do we verify that? So that's equal to, with z hat delta of x delta of y. Is that 0? Why is that 0? Is it 0? So that's z hat dotted with gradient. What is z hat dotted with gradient, operator?
1.
DDZ.
DDZ, right? Z hat dotted with gradient is nothing but d by dz. That's it. Only that survives. So that's d by dz of, like, I can move this to the left, right? Z hat times delta of x delta of y. That's surely 0 because whatever this is, I don't know what that, I mean, it's a very not a nice function, delta function, but that's whatever that is, that's 0, right? But that won't work for this anymore, right? Because that has the z dependence in it, z prime dependence in it. So clearly this is not a magnetostatic situation. The moment you have sources, you're not in magnetostatics, right? But we're still working in it. We're saying that it's really far away, and we will try to avoid it as much as possible. And we will, so under what conditions are we? Is this going to work? Our observation point, right? Magnitude of this should be very much less than L. So we shouldn't be going here. So as far as you're in this region, right, then you're good. So if you get very close to within 10% error, 1% error, then you're good. So if this is, if the length is 10 centimeters and you are working only in 1 centimeter, that's 10% accuracy. Right? 10% accuracy, this approximation is correct. If you want more accuracy, you get closer to the wire and will simulate an infinite thing. So that's the kind of thing we're talking about. So, okay. So with that, now again, there is delta function, right? So we can do these things. Two of the integrals can be done, x prime and y prime. And z prime, z hat can come out, right? That's just a constant vector. I can come out. So this is equal to z hat times mu naught I over 4 pi. Complete the integral of x prime and y prime, basically sets 0 x prime and y prime. And I should also put this theta function there, right? Put that prime L. That's dz prime minus infinity to plus infinity, and there's only divided by x squared plus y squared plus z minus z prime squared. Okay. this survives only when you're within this region. Otherwise, it is 0, right? And whenever it survives, it is 1. So that's the same as saying, I think, yeah, give it one more minute. Oh, something got striked out. I think they could manage it. Okay, so that's the same as C hat mu naught I over 4 pi. Notice if you're outside this region, that's 0. If you're inside that region, it is 1. So that's the same as saying this is minus L plus L, because only then it survives. Otherwise, it's 0. And whenever it survives, it's just 1 divided by x squared plus y squared plus z minus z prime, the whole square root. X squared plus y squared is nothing but rho square, right? That's the cylindrical coordinate. X squared plus y squared is rho square, right? That's the cylindrical coordinate. That's just not really necessary, but gets rid of one or more compact. That's all. Okay. What is that integral equal to? What would you substitute? A substitution could be, there are two various ways of going about it. Like whenever there's a plus, tangent theta is a good one. But since it's a square root, if you do a tangent theta, it comes out as an integral of 1 over cosine theta. And then you have to do that. That's also doable. But instead, it's more straightforward, you do sine hyperbolic, right? So let's say z prime minus z is rho times sine hyperbolic theta. Let's make that substitution. And the z prime then is equal to rho times cosine hyperbolic theta. Theta. That's all. And let's do that. So that's equal to z hat mu naught I over 4 pi when z prime is equal to minus L. Right? You have minus L minus z divided by rho, that's your theta, and then you have to take a sine hyperbolic inverse, right? So this is equal to sine hyperbolic inverse of minus L minus z over rho. That's a lower limit. And the upper limit is sine hyperbolic inverse of L minus z over rho.
Is there a reason why you did z prime minus z?
Yeah, so that I can get away with this minus sign. You can substitute the other way, that's okay, because this is a square, right? It doesn't matter.
Yeah.
Right? So yeah, I mean, you can do the z minus z prime, but then this will have a minus sign.
Minus sign. Okay.
Just to avoid a extra minus sign in there. Yeah. Like again, this will have, there is a minus sign in here. It's just a little less number of minus signs. That's it. That's all. But overall, it should work. Yeah, good point. So the limits gets really messy, but the integral becomes easy, right? dz prime is rho cosine hyperbolic theta, d theta. And what's the denominator? So if I substitute this to be rho sine hyperbolic square theta, what is the denominator? So the denominator will be rho square plus rho square sine hyperbolic square theta, right? Which is equal to 1 plus sine hyperbolic square theta. What is that equal to? 1 plus sine hyperbolic square theta?
It's just cosine.
Cosine hyperbolic square theta. And you take square root, which is again rho cosine hyperbolic theta. And they all cancel out. I think that's the advantage of this. They all cancel out, so the integral becomes trivial. Right? It's just the subtraction of the limits. So if you allow me to write that, so that's equal to z hat mu naught I over 4 pi times sine hyperbolic inverse of L minus Z over rho and minus, it's still within the book, minus L minus Z over rho. Sine hyperbolic of minus x is actually x itself, so I can pull out this minus sign and change this sign, so this is plus. That's not a convenient form. We will process this more. Remember, we have to take this limit, right? This is a correct solution. That's perfectly correct solution. One point I want you guys to notice is that this is in the z hat direction. Usually the A is in the same direction as the current itself. Like at least locally speaking. If they're more, if the current has a unique direction, then it will be in that direction. Otherwise, they will have to add up in a sense. But we will process this and get it much simpler because we want to talk in terms of limit L tends to infinity, and there is a lot of simplicity in there. And that's what we will focus on. In your homework problem, you don't need this information. I directly give you the expression for B, magnetic field, for this finite wire. So start with that expression and you should be able to proceed forward. Right? And basically what I ask you guys to do is that you know the magnetic field for one finite wire. Put another wire, another wire, another wire. So then you can make a loop, right? Okay, then you can talk about the magnetic field right at the center of the square. Right? Contribution from this, and you can get that. Then you can do this for a pentagon. Right? Again, do this at the center. You can get that answer. You can do this for an hexagon. In fact, you can do this for an n-sided polygon, regular polygon, and in the limit n tends to infinity, it should become the answer for a circle, right at the center. So that's what you do in the homework. It's kind of a neat, it comes out relatively simple. Remember, sine x over x, that's the limit x tends to 0, is equal to no?
1.
Yeah, 1. Yeah. You guys took a long time, I was worried. Right, it's equal to 1. That's like in the limit n tends to infinity, you will get such a limit. Right, that's all the trick that you need. Yeah, so that's all I suppose. I think that's all there is to the homework. So yeah, it's due on Tuesday. The first two problems, I think, in the first part of the lecture we covered. The one that does with the regular polygon, I think, and it's available all around. It's a problem from Griffiths which I have broken it into many pieces. So it should have been discussed various places. So you should be able to get help on that. But it comes out reasonably simple. Okay, that's all, I suppose. Anything else? Michael, Jordan, how are you guys? Michael, are you here or are you?
I'm in Kansas right now, but I'll be in Illinois on Friday night or Saturday.
Okay. So your TA duties require you to be here, right? Otherwise, probably the courses you can.
Yeah.
Yeah. Jordan, more things?
Good. Surviving.
Okay. Okay. Enjoy.
Thank you.
Thank you.
Thank you.
You-
Yeah, I had forgotten the exact identity, so I was doing L'Hopital over my head.
Ah. Okay.